So now let's think about our previous lecture, lecture 10. In lecture 10, we have introduced very important approximation called as GCA, gradual channel approximation. What was the meaning of gradual channel approximation? In order to consider the electrostatics inside our MOSFET, in general, we have to consider this entire three-dimensional structure. However, we believe that along this width direction, at least in the case of our planar MOSFET, everything is just homogeneous. So we can just neglect these z-directional dependencies. So now we can reduce it to just 2D problem. Draw just a cross section and solve entire system. When we have a look at this 2D system, actually you can find that there is a gate and also substrate or body, and also here we have a source and drain. They are all different contexts, gate, source and drain, and even doping profile can differ. For example, here we have N plus region and N plus region, and this is a p-type region. However, considering this entire 2D system is too much for our purpose, so our simplification was, okay, among them, the most important part is just intrinsic channel region, excluding this source and drain. So now simplify this way, just having one gate separated by oxide and uniformly doped p-type substrate. That was our simplification. After that, yes, it has some quantities like x-directional variation over x-directional electric field and y-directional variation over y-directional electric field. We had to consider these two different quantities for our 2D calculation, 2D Poisson calculation, but the central part of gradual channel approximation is this second term, the lateral or channel directional component of electric field variation is relatively small than this vertical direction. So the vertical direction actually determines the carrier distribution. That was the gradual channel approximation. Yes, now we can do it in this way. Then if we neglect this term, then what we can have is now epsilon over mu, silicon permittivity and mu, and this mu can have also three different components like electron or hole density, electron density and doping density. We believe that this is uniform and can be treated quite easily, and in the case of yes, these two, they are really position dependent. But problem is, in order to calculate these two quantities, we have to know electrostatic potential as a function of vertical and lateral position, and also in order to calculate electron density, we must know electron quasi-Fermi potential. Or if we wanted to know hole density, then we have to know these quantities. But what was our understanding on these two, especially these two quantities? So electron quasi-Fermi potential and hole quasi-Fermi potential. In the case of hole quasi-Fermi potential, this is entirely determined by just body contact, substrate contact, which is just grounded. So even in this general case, we can certainly say that yes, hole quasi-Fermi potential is equal to the body voltage, substrate voltage equal to 0. That was done. And now the remaining part was this one. Well, we have to actually calculate this electron quasi-Fermi potential as a function of general 2D position, but great simplification was possible because now we say that although we have to calculate actually this 2D wise calculation, but it can be reduced as just 1D like or channel directional calculation. So that was possible because if we allow any kind of change in our electron quasi-Fermi potential along, for example, x direction, then that means that if this is not 0, then we will have vertical current conduction, which is quite easily counterintuitive in our structure. So that's the reason why we have to say this is equal to 0, means that phi n is not a function of our x position. So now, starting from this general 3D structure, by adopting these approximations, now our understanding is like this. We have to solve the intrinsic part of our transistor, and it can be divided into several pieces, which is usually called as slabs. So here we can find several slabs, and this position is corresponding to the source contact, and this position is corresponding to the drain contact, and here we have body or substrate. And important one is inside this slab here, for example, corresponding to a certain y value, here we can define a unique value of electron quasi-Fermi potential written as a V of y. So once we have this given fixed number of electron quasi-Fermi potential, then now calculation of electron density can be quite easily done, quite similar to that of equilibrium case, only shifted by this electron quasi-Fermi potential. That was the main finding of our previous lecture. So do you have any question on? Okay, please.
그 vertical current가 흐르지 않는다는 거는 델타 x분의 델타 v가 0이라는 뜻과 동치어가 맞을까요? 델타라기보다는 편미분 v가 0이라는 것과
Yes, actually this one is nothing but just showing that quantity. So when you write down, it is corresponding to phi n ex, and this is in this presentation material I use V to represent electron quasi-Fermi potential. So your expression is corresponding to the vanishing vertical field, x directional field, x directional current.
제가 저번에 수업 끝내고도 한번 여쭤보긴 했었는데, 그럼 저거가 0이라는 것과 그 편미분 x분의 편미분 ex는 0이 아니고 존재하잖아요. 그 맨 왼쪽 밑에.
So this one?
분자가 ex입니다. x분의 ex. 네, 그거는 0이 아니잖아요.
Yes, of course it's not. Of course.
둘 사이 관계가 제가 바로 좀 이해가 안 돼서.
So this is this ex is obtained as minus. So x directional derivative of electrostatic potential. This is electrostatic potential, and this is a electron quasi-Fermi potential. So although we take first order or second order derivative with respect to the x directional position, but starting function, these are different. One is electrostatic one, and this is electron quasi-Fermi potential, so they are completely different. So although it simply means that although we can allow electric field variation along x direction, but we cannot allow variation of our electron quasi-Fermi potential. If we allow it, then we must have certain current conduction. Although we allow electric field, x-directional electric field, or sometimes change of electric field, that doesn't matter. That is not directly related to the current conduction. Please think about your p-n junction. In your p-n junction, you have quite strong built-in electric field, and also electric field varies quite rapidly inside your system. So you have electric field, at the same time change of your electric field, but that does not necessarily mean that you have a current conduction. The condition for having zero electric current and Hall current is quasi-Fermi potential, and quasi-Fermi potential for electrons and Hall should be a constant. It means that gradient vanishing. Then you will have zero current. So so if you don't understand the difference between quasi-Fermi potential and electrostatic potential, actually in my opinion that is quite important lesson you had to learn in your previous lecture. And please visit our lecture material, review material, lecture 3, I guess, at the end of our lecture material, lecture 3. So I try to at least show some formulation about our electron quasi-Fermi potential and Hall quasi-Fermi potential. Please review that part. Yes, so actually that concept, the difference between these two components, seemingly both of them are called as potential, electrostatic potential and electron quasi-Fermi potential. Looks quite similar, however they are completely different, so you have to understand their difference clearly. Okay, good question. And any other question for reviewing our previous lecture? So once we adopt this kind of consideration, then now the situation becomes a little bit more simplified. Now what we have to do is, well, although we have no idea about what is the exact value of V at Y, but anyway we can try to, for example, for this slab there is a certain value, and for this slab we can define another value. Also any slab we can at least assign a certain quasi-Fermi potential value. So what is the exact number? We have no idea up to now, but anyway we can try to introduce a set of new unknown variables. And other one is there are boundary conditions. So what will be this V at Y equal to 0? That is exactly equal to the source voltage, as we discussed previously. And in the case of our drain end, please try to estimate the boundary condition for our electron quasi-Fermi potential. This Y equal to L is corresponding to the drain end of our channel. In this case, since this is connected to the drain, its quadriform potential should be regarded as drain voltage. So although we have no idea about what is the exact value at certain position, but at least at two extreme points, so left and right end, we know given well-defined value, and our aim is to find out the values shown here. And once we assume certain number, for example, let's say that happen to be 0.1, then next calculation is quite much straightforward. Now this system can be regarded as just a single MOS capacitor. Why we can treat it as a MOS capacitor? In general, we have to consider electric field between communication of electric field between this central slab and left slab and right slab. But we neglected that electric field component. What was the approximation? That was actually gradual channel approximation. By considering gradual channel approximation, we just neglect this electric field component. So now we can just consider only one MOS capacitor independently. Yes, here we have a different slab and it may have different quadriform potential. Then we can treat it quite separately. There exists another MOS capacitor and its electron quadriform potential has different values. Let's say that this one is just 0.01 instead of this 0.1. Then now we can imagine two different MOS capacitors. In terms of their structures, they are identical. They have a certain length scale and given oxide thickness, and also even applied gate voltage are shared. The only difference between this one and the other one is inside the left one, quadriform potential is relatively low, and for the right side one, we have a relatively higher quadriform potential for electrons. Then what happens to these two different MOS capacitors? Let's assume that they share exact same electrostatic potential. Say that this is the electrostatic potential X position, and happen to be this is phi, and also this is X position and happen to be the exact same profile for our potential. Then what happens to these two steps? What we can expect is, well, in terms of our hole profile, hole P, they will show the exact same hole profile because they share the same hole quadriform potential. But since they do not share the same electron quadriform potential, what we can say is this left one has higher electron density, and this one, the right one, has lower electron density. Why do we have this kind of behavior? Because electron density is inversely, exponentially dependent on the quadriform potential. If we have a higher quadriform potential, that will reduce the electron density when we have the same potential profile. So simply means that in order to maintain the same amount of charge, what we have to do is, or what this left or right slab have to do is it should have increased potential profile to maintain the same amount of electronic charge density. Otherwise, if it has the same potential profile, then its electron density will be reduced. Okay, so that is the situation we will have. Anyway, in this 2D system, simplified this 2D system, now previously our task was to calculate, solve two-dimensional MOS equations, but now it becomes just solving several MOS equations, and solving one single MOS equation, it is relatively easy. You can do it. You have already done it. So what was it? You have found that potential, surface potential actually determines the charges inside the silicon substrate. You have a well-known expression, and the only modification you have to do is, in that expression you have a electron related part, and that electron related part was modified with certain form like V over Y kBT over Q. By adding this factor, now you can consider modification of your electron quasi-Fermi potential at a given slab. That was the situation up to today's lecture. Okay, so now we are ready to talk about the real 2D structure. Now we know electrostatics. Up to now, have we considered the movement of electrons? Actually, not. What we have done was only 2D Poisson equation. Poisson equation is nothing but just Coulomb's law. It just describes the number of our net charges and generated electric field. We don't care about the movement of our electrons and holes. So now it's time to talk about the current itself. And if you visit once again our lecture material, L3 material, then you can find that this kind of expression. Electron current density. Electron current density is the quantity defined as ampere per square centimeter per unit area. How many current is currently flowing? That is described by this current density. So in order to get actually terminal current, what you have to do is integrate this current density over terminal area. Once again, let's just think about this one. Now I'm trying to draw a magnified view of our system. So let me just draw silicon. Let's say that this is the surface of our silicon substrate, and here we have a certain pillar, and this pillar is corresponding to our drain. Yes, this is drain metal contact. Of course, it is biased to VD. Then our question is, we must calculate drain current. Then how can we calculate the drain current? Then maybe you can think that okay, if we are talking in a level of circuit schematic, then how can you define drain current? Yes, this will be drain current. Yes, in terms of our circuit schematic. Then, in terms of a more magnified view, more microscopic view, how can you understand this drain current? This part is now magnified in this way, and this drain terminal is shown here, and the contact between drain terminal and our silicon channel is shown here. Now you are looking at this interface. Then how can we define, once again, drain current? That should be done in this way. As you know here, as you already know, drain current is defined as the current flowing into the transistor from external circuit into the transistor. So we have to consider the direction, current direction heading in this way. Here we have the inside part of our device, and this is the outside of our device. So we must calculate the current heading this direction. Then how can we calculate this component? It is quite obvious. We wanted to calculate the drain terminal current. So now we have a drain, and we must integrate over drain contact. And if we consider electronic contribution, then this current density should be surface integrated over this drain contact. So let me just illustrate it. What does it mean? In this silicon substrate, we can define any arbitrary position R. Then at this arbitrary position R, we can define also current density vector J sub n. Yes, we can define this quantity everywhere inside this system. And also we can define same quantity at this point, that point, the point attached to our interface. So now we can define these vectors for everywhere. So then now let's assume that there is a certain vectors like this. Yes. If we have these vectors, then what we have to do is we must integrate this Jn vector on the drain contact. What is the drain contact? So the part shown here as green shaded plane. This is the interface between, or contact between, metal and silicon substrate. Over this green part, we must calculate this Jn. And of course, please be noted that if you just perform this one, then you will have the direction like this. Usually this dA direction is outgoing direction, but your drain current should be positive when current is flowing from outside into the inside. So you must add this minus sign finally. This is the expression for your drain current. You can try to do it for every other terminals. For example, I wanted to calculate a source current instead of a drain current. Then what you have to do is, instead of this subscript source, you can just introduce a drain. You can just introduce a subscript S, and that integration is not done on the drain contact, but you have to perform this surface integration over source contact. That's it. This is general expression. If you wanted to have any kind of terminal called as alpha, then you have to perform the surface integral over alpha terminal. Then that's it. For example, alpha can be a body. Okay. So up to now, I just introduced the general expression for or general definition in our sense, definition of a terminal current. And now you clearly understand this terminal current. This terminal current is the quantity of our interest, but it can be related to what? It can be related to the current density. Ultimate goal is terminal current, but in order to calculate terminal current, we must understand current density inside the system. That is the important one. Now let's just say that we wanted to know the number of persons just passing through that lecture room entrance, lecture room door. In order to, for example, now let's think about this way. Let's say this, assume that here we have a room and there is a door, and let's say that the number of persons passing through this door is quite important. Let's assume that for 1 hour. Although what we wanted to know is just the number of persons crossing this certain surface. In order to predict the number of persons, then what we have to do is how many persons are moving there. If we don't have any kind of information, then we cannot understand the outgoing flux. For example, let's say that this room is completely empty. Then after 1 hour, what will happen? There will be no outgoing flux from this empty room. Instead, let's say that this room is full of students. Then what will happen? After 1 hour later, there will be so many students escaping from this lecture room. So although our interested point is only here, door, or in our case, drain contact, source contact, or body contact, but in order to understand the quantity at that point, drain contact, we must understand the entire system. Otherwise, we cannot get the precise information, because that door or drain source are not a separated object that is connected to the other entire system. So we must understand this entire system, and as a result of that analysis, we can understand how many students are escaping from the lecture room, or how many electrons are flowing through this drain contact. That is important one. So now we understand, in order to calculate the drain contact, we have to calculate current density, and current density has the form of this expression. So current density vector is proportional to the gradient of electron quasi-Fermi potential. Of course, if we consider whole current density, we have to consider gradient of whole quasi-Fermi potential. And here we have electron density, and here we have whole density. That is quite natural. And in our 2D structure, 2D planar MOSFET, then this Jn can have x directional component and y directional component, of course. However, we can safely neglect this x directional component. Why? This is not allowed from our structure. If we allow this one, then from interface, into deep substrate, we allow current conduction. It never happens. So only we have y directional component. And now you are looking at this y directional component only. Although it is written as just a scalar number, this is y directional component of our Jn vector. And what is the x directional component of our current density vector? It vanishes. You must understand this assumption. Then now here you have quite a simple expression. Q, mu, n. This is mobility and this is electron density. It's okay. And what is it? This is nothing but just a y directional component of a gradient of electron quadriform potential. This is nothing but just this one, y directional component. And now we have this form. Of course, we have to use partial derivative, but happen to be, we assume that v in general a function of x comma y can be also expressed as just y, a function of y. So now we can use this total derivative without any problem. So now we have this one. Then please allow me to explain a little bit further about this equation tower, equation 3.5. Well, it says that this is a function of two positions. So let me just draw two-dimensional structure once again. And let's say that this is y equal to 0 and this is y equal to L. Source end, drain end. And this tower equation 3.5 just says that if we select any point x comma y at any arbitrary point, then that will have just current only y direction, and amount of this y directional current density is simply given as this one. This is the expression we wanted to have. So what is our interested quantity? As I repeat again and again, what we have to calculate is drain. Here we have a drain. So we must calculate actually the current density at this drain end. However, this expression is generally valid for arbitrary position. Any arbitrary position we can write down in tower equation 3.5. Okay, then now please have a look at this equation 3.6. Now we introduce drain terminal current. How can we calculate drain current? So of course we must integrate our current density over x directional. That will be the drain current from 0 to infinity. We must do it. But if you are careful, or if you are following my lecture progress, you will find that my previous statement is somewhat wrong. I mean that I emphasize that in order to calculate drain current, we must perform the integration over drain contact. Please have a look at this one, this expression. What does it mean? It means that just a given y position, vertical integration is done, and is there any condition for specific value of y? So y equal to 0 is not allowed it. Y equal to half L is not allowed it. Or y equal to 0.9L is not allowed. There is no such kind of restriction. I'm saying that for arbitrary value of our y value, we can just perform this vertical integration, and I say that this is corresponding to ID. Please let me just emphasize its meaning once again. It means that I'm just performing at arbitrary y value this vertical integration and say that this is corresponding to ID. And if I change just y value, I'm saying that the result of this vertical integration should be also ID. In my opinion, actually this is not the case. The real drain current should be, where can you find the real drain current? The real drain current is found only when you perform the integration at y equal to L, the drain end of your channel. But why I'm performing this kind of integration for arbitrary y value? That's the problem. In my opinion, by definition, only this one is the correct one. But I'm calculating the current at arbitrary surface and say that they are all the same. Since they are all the same, if I calculate it here or there or any position, this one gives us the correct value of ID. Why we say so? It is related with quite powerful law like current conservation. If we say, if we say this value, this integration value can be different from that integration value, and that can also differ from the other one, that allows us that electrons are entering into a certain position and the flux is not conserved at all. So after time elapsed, the number of electrons are increasing or decreasing. But this kind of time dependent behavior is not considered in our today's lecture. We are considering, simply speaking, we are just considering DC condition, steady state condition. So in this steady state condition or DC condition, everywhere we must have the exactly same amount of current. So now let's think about this one. We have a chain of serially connected resistors, and here we have grounded, and here I applied VD. And let's say that here we have 1 amp, and here we have 2 amp, and here we have 3 amp, here we have 4 amp. Is it allowed? Obviously not. So we must have the exactly same amount of current flowing through our small pieces called here written as resistors. So quite similarly, if we just come back to our 2D MOS system here, if we say that there occurs 1 amp, and let's say that this is 2 amp, and let's say this is 3 amp, that is not allowed. We must have a constant value. Of course, we can verify more mathematical formulation, but I will just skip it. So intuitively, we can understand, although we can perform this kind of vertical integration everywhere, but regardless the position of our y value, we must have a constant value. That is the key point here. This is just position dependent quantity. You can evaluate this quantity everywhere. If you want, you can do it even at y equal to 0. However, what I wanted to say is that should be just a number which does not depend on your y. That is the key. So please have a look at this part. So is that, yeah, yes, here we have this one. ID, now it is not corresponding to y anymore. Then what happens is here ID is a function of y and it is actually a constant. Then what they have done is just to integrate this left hand side and right side from 0 to L, from 0 to L. So are you with me? Then if we have a look at this right hand side, this is just a constant over y. So this calculation becomes just L times constant ID. So simply speaking, what we can say is ID is given as 1 over L and integrated ID, position dependent ID expression, and that will be the expression for our entire system. Okay. Do you have any question? So please try to understand the main message of my today's lecture. Terminal current. The quantity of our interest is once again terminal current. But terminal current is unfortunately all coupled with internal physics. So therefore we must know everywhere inside our system. So that can be done by this calculation. Our terminal current measured at terminal is related to the internal quantities, and this internal quantity is just given as what? Internal quantity is given as this kind of simple expression here. We have a W factor here, but the W factor is just multiplied along G directional homogeneity, and now we have only X directional calculation. But fortunately, we can make even further simplification. Well, we must do the vertical integration, X directional integration, but this dV over dy is not a function of a vertical position because V itself is a position, y position dependent condition. So this is not a x dependent one. So we can further evaluate it in this way. Q W dV over dy and integrate mu n dx. What I have done is just to pull out our dV over dy because this is a constant over a given y value. Then here we have introduced another simplification. This is also important. Here we have the quantity called as mobility, and unfortunately this mobility itself is a position dependent quantity. Yes, it's true. It is actually very sensitive quantity, sensitive function of a position. But what we have done is like this. Please have a look at this way. Q, W, yes, dV over dy. They are just leading coefficient, and we do some trick. This is the trick. So here we have n dx. Since we have newly introduced n dx and integrated n, also we introduce n dx here. Please think about what I have done. I just divide our equation by certain quantity and once again multiply that exact quantity. what I've done is just the identity. So I have not changed anything in this case, and we say mu n and dx. Are you with me? So did I make anything wrong? So as much as this integrated electron density is a positive number, I am allowed to do this job. If there is no electron at all at a given MOS capacitor, then I'm doing wrong. But you know, there is always a positive number of electrons, so this quantity can be regarded as always a positive number, so I am allowed to do that. Then later, please have a look at this quantity. What is this? This quantity is just integrated a product between mobility and electron density, and it is divided by, once again, integrated electron density. So the overall dimension of this expression will be a certain mobility quantity, because you know, although here we make integration is done in upper and lower, and electron density also appearing upper and lower, they are all cancelled out, and we have a certain mobility quantity. Yes, previously mobility has severe position dependence. However, by performing this kind of calculation, now we say that this term can be expressed as a simple number called as effective mobility. So now once we introduce this effective mobility, then things becomes really simplified. Then now we can say that drain current at a given, or any current at given y position, can be expressed as this one. This dv over dy factor was pulled out, and also we introduced mobility, and the only remaining thing is integration of our electron density over vertical direction. Now you are looking at this one. Integration of our electron density along vertical direction. Combined with this minus q, the electronic charge, then this one simply gives us the total amount of inversion charge density. So please, Qi is originated from only electrons in our N MOSFET. So it is difficult to expect this kind of electronic charge in our p-type substrate, but due to the inversion phenomena, we can expect this Q sub I. Then now we can say this is the expression. At any position y, we can express our current in this way, and that should be actually a constant of y. Well, up to now everything looks perfect, but there is a hidden point. When I introduce mu effective, what was the trick? So mu effective was defined as mobility electron density divided by electron density integration. However, that integration is evaluated at a given y value. It means that if we just consider different y position, then unfortunately also this mu effective can be a function of position y. But for further simplifications, in many cases we just say that okay, this mu effective can be regarded as just a constant even for every y position. Yes, that is the thing we are doing currently. So please understand our hidden approximation. So now let's treat this mu effective as a real constant at a given problem. Just treat it as a given constant. Okay. So that's the way we have done. So then let me just write down in this way. Then ID can be written as, if we come back to the previous expression, this is the expression for ID, mu effective W that is required. So WL mu effective is pulled out, and here 0 to L, and dV over dy qi, that integration is required. But when you have a look at this part, then you can find that dy and dy occurs twice, so they can be transformed into different form. In terms of dy, it varies from 0 to L, from source to drain. But if we convert it to, let's convert it to the dV integration, then that can be dV and integration of qi. And from source side to drain side, our electrostatic potential changes from what to what? From source voltage to drain voltage. So that's the reason why now we have this expression. ID is just written as certain numbers, blah blah blah, and just to say that integration of our inversion charge density. But inversion charge density is not integrated in, how can I say, with respect to the real space position. Why? But integration over this electron quasi-Fermi potential. The lower bound is source voltage and upper bound is drain voltage. So in this presentation, we assume that source is always grounded. That's the reason why we use 0 and VDS, but in general, it should be VS and VD. Okay, so this is the expression. So this is quite general. You understand the approximation we have done. The approximation we have done is like this. In order to allow this one, this mobility should be a constant. If mobility is position dependent quantity, then we will have some errors. And actually mobility is a position dependent quantity. So this is not exactly the truth, but well, anyway, mobility, we just pull it out and say this is shown here. And now we have just integration of charge density, inversion charge density as a function of this electron quasi-Fermi potential. Yes, so that's the reason why our goal is now find out the functional form of inversion charge density of a function of this electron quasi-Fermi potential. Once we found this expression, then just integrate it. That's it. So this is the first part of our today's lecture. Of course, I spent some time for reviewing our previous lecture, but after that, we introduced the expression for drain terminal current. And what we have found that is, okay, drain current can be just obtained as integration of inversion charge. But please don't be confused. Integration of electron charge over real space. No, this is integration of electron charge over our electrostatic potential. That is required in this calculation. So we must find out this functional form. Are you ready? Then let's do the next part. So already we have one integral. Yes, Pausa double integral just means that in order to calculate drain current, we must perform the integral twice. That is Pausa double integral. And already you can find that in order to calculate drain current, we must perform one single integral for our dV integration. Then what is the next thing? Actually this one. In order to calculate Qi, we must perform once again a certain integration that is shown here. So Qi, this is electron contribution to the silicon charge, and simply given as electron density integrated over along the vertical direction, and that can be also variable change. Here, although dx, it can be written as this way. This is, once again, this is potential. Phi is potential, and you know, this is nothing but inverse of our x-directional electric field. So this is corresponding to actually -1 Ex. So you can see that here we have Ex, 1 over Ex and d phi. And here we have electron density. Electron density is simply given as its original form, usual form we assume. So Ni squared divided by Na. What is it? This is nothing but the electron density and x equal to infinity. This is an extremely small number. So now you can see that this is the general expression. Any simplification? Unfortunately, no. There is no simplification. Just to put out our already known result. Then by combining this Qi and our previous expression for ID, so let's just insert it here. Then what will happen? That is the famous Pausa double integral. So you can find that there exist two integrals for electron quadriform potential. Although it is written as dV, this is related with channel directional integration. So this is kind of y-directional integration, not exactly same. And how about this d phi? D phi is related with actually x-directional integration. Please note that by combining these two, Ex is d phi over dx, and here d phi, so it can be converted into dx. So simply speaking, when you have a look at this Pausa double integral, at first glance you feel that, oh, this is too overly complicated. But if you just have a look at it step by step manner, then you find that this is nothing but just two-dimensional integration of your current density. Two-dimensional integration, dx over dy should be performed. However, this dy is converted into dv, and also this dx is converted into d phi. So that is the one you have right now in this quite complicated form. This is a Pausa double integral. So, and in our sense, this Pausa integral, Pausa double integral is regarded as a golden rule. So this is quite rigorous, and we have not introduced much approximation. Maybe you can ask me, already we have seen many approximations, gradual channel approximations, and neglecting vertical current component, and also mobility is regarded as a constant, whatever. However, this is not that big deal. So we believe that this is rigorous enough to be used as our reference. So this is Pausa double integral. Okay, we have only 8 minutes left, and for remaining 8 minutes, I will try to demonstrate that how difficult to actually evaluate this Pausa double integral. So the reason why I'm showing you this difficulty is later from our lecture 12, we will introduce so many approximations. So to make it more addressable, but maybe you feel in this way, well, this is just approximations. I don't like it. I want it to be a rigorous analysis, but unfortunately, rigorous Pausa is quite demanding when you try to calculate it. This is the motivation. So I wanted to just justify why we are living with the approximations, because it is easy, make it easy. So now let's go to this one. Oh, by the way, so in this case, when you perform this x-directional integration, actually we have to start from 0 to infinity, and if it is converted into, for example, dx over dy over dy, then we have to find out the bounding values at 0 and infinity. Of course, if we go to this infinity, then potential will be just 0. And if we go to this 0, position equal to 0, then what is the value of potential at surface? That is called as surface potential. So in order to perform the Pausa integral, anyhow, we have to find out the surface potential. Then how can you calculate the surface potential? Yes, we already know how to calculate the surface potential. So before performing this Pausa equation, first of all, we have to solve. This is already a little bit simplified because here we have in total 6 terms, but 2 major terms are kept here. But anyway, first of all, we have to solve this MOS system. Then find out phi s at a given position. Then that given position under given b value, then by using this given electron quadriformity potential, we can calculate the surface potential, and we will use this one, because when we have a look at this Pausa integral, here we have a double integral, and when we perform this inner integral, we have to say that electron quadriformity potential is a given number. So now this is a given, and this is a given, and also this phi s can be calculated from given electron quadriformity potential. So for given electron quadriformity potential, evaluated these quantities, after that taking this integration. So just showing you this, you can do it, but let's do it together with me. Okay. So I have prepared a simple code for you. Now, of course, this is optional, so when we approach to the end of our lecture, I will just stop. If we, for example, try to calculate the ID at a certain bias point, this is somewhat arbitrary. So if you want, you can test any arbitrary value, for example, high gate bias and moderate drain value. Then how can we actually evaluate this Pausa double integral? Then please have a look at this expression. This expression is now, what is it? There is no double integral. There is only one single integral. And why? Already in this expression, I convert our outer integral, the V integral, into just a Riemann sum. So you can see that here. This is a Riemann sum, and this is corresponding to our dV, and this summation is corresponding to our integral. dV integral is just converted into Riemann sum, and you can easily, if you try to implement it by yourself, then please check whether your integration can be done correctly. I assume that you can do it without much difficulty. After that, since this dV integration can be easily done by Riemann sum transformation, then the only remaining task is this inner integral over potential. Then how can you do that? First of all, we have to evaluate this integrand at a given phi value and perform this adding up the Riemann sum once again. However, we must stop at this bounding value phi sub s. One way is, before starting this integration, first calculate the phi s and stop there. Right, that is one thing. But in order to calculate the phi s, usually what we have to do is adopting the Newton method, but I don't want to bother you any further with the Newton method. So in this presentation material, lecture material, I have prepared how can you avoid or detour the adoption of Newton method. So please, if you are interested, please have a look at it. And by performing this kind of integration, so this is phi integration, and it can be also converted into Riemann sum. And here I have introduced a specific value of delta phi. But this is just a 1 millivolt case. You can adopt different values like whatever, 0.1 millivolt. And by performing this kind of all kind of thing, then you will eventually find certain drain current. So simply speaking, if you perform this Pausa double integral, at least first of all you need computer and some coding, and for that purpose, the most critical part is finding out phi s as a function of given electron quasi-Fermi potential. So once you calculate it, after that you can just perform the Riemann sum twice, then you will have the value. This is the value. And also I have make a comparison with this Pausa integral result and more elaborated ticket simulation, and they shows certain close resemblance. So this dot is Pausa, and this line is computer program simulation. And maybe you feel that, oh, they look similar, but already they show some differences. Oh, why do we have differences? Maybe Pausa equation is not that perfect. So in this case, it's not. Pausa equation is, in this case, good enough. The reason why we have small differences here is this is the my ticket structure, and I assume that our length is 1 micrometer. Please find out 1 micrometer. Where can you find 1 micrometer? In this case, I started from this 50 nanometer and ends up this 1.05 micrometer. That was my 1 micrometer long structure. So simply speaking, this is our entire structure in my ticket simulation. And how does it look like? Is this uniform or non-uniform? Of course, at the majority of our structure, the quantity looks quite uniform. However, here we have a source, and here we have a drain, and at the boundary between source and channel, and at the boundary between drain and channel, here we have quite unexpected behavior of our electrostatic potential. What does it mean? So our assumption, when we start, we just say that, okay, we can neglect the source and drain and consider only central part of our intrinsic transistor. And what is the central part of our transistor? Actually, this is the central part of our transistor, and there exist transition regions between source to channel and channel to drain. That's the reason why we have small differences here. Instead of this L length equal to 1 micrometer, if we increase it to 10 micrometer, that difference can be reduced further. And if we go to the extremely long channel device, then of course that difference can be completely neglected. Okay, so anyway, let me just summarize. Today we have introduced pausa double integral. This is theoretically very important, practically not used at all. However, theoretically very important, and our later development, lecture development will be based on this pausa integration. We will try to introduce further simplification to this pausa double integral. So please do your study in your dormitory room, and let's have a look at once again. Okay, thank you.